Hi, everybody. I actually don't speak at too many conferences, but that's very nice, very generous. So my name's Habib. I'm a data scientist at Transferwise. And I guess today I'm really excited to talk to you guys about how we approach machine learning solutions, and in particular how we design our solutions to be what I call flexible. All right, so before I get started, I'm just going to talk a little bit about Transferwise and what we do. So Transferwise was founded by two Estonian software engineers. So we're actually quite well known around these parts. But for people who haven't heard of us, we're an international money transfer service, which means that we help people and businesses transfer their money around the world. Okay, and often that involves converting their money into another currency and making sure that that money lands in the right account in another country. And we do that cheaper, faster, and more conveniently than anybody else. All right, and we're often using machine learning, and we're always asking how can we use machine learning to make that experience just more enjoyable for our customers. Cool, so now I'll talk a little bit about what we do in the data science team. So whenever we're going from problem to solution, we always make a real point to actually just pause and really consider the problem, and really consider the problem's core aspects. So what are the key things that we need to solve in any given problem? Okay? And I just wanted to stress that point because I think there's sometimes a tendency when people are approaching a new problem and want to approach it with machine learning to almost have like a favored approach or an approach that they're very familiar with and want to apply that approach to almost every problem that they see and encounter. And what happens when people do that is they end up modifying their problems so that their problems become fit for the solutions that they want to implement. And I think rather than being solution-driven, we should always be problem-driven. So it's a real thing that I guess we make a real point of trying to consider at the beginning of each project. The other thing I just want to say about this is that it can also be interpreted as the problem is greater than the solution. Okay, so you can build the best solution to a really small problem, and likely you're just going to have, you're going to be limited in terms of how much impact you can have. Okay, so it's important to focus on the bigger problems. But later on, I'm going to argue that perhaps we can actually reverse this equation, and we can figure out a way to make our solutions more impactful than the problems that they were originally designed to solve. So we'll come back to this. I think a good starting point whenever you're in this phase of trying to develop a solution and considering using machine learning is to really ask this question. I think it was asked by somebody in the crowd earlier. And I think it's a really important question, and it's a really important thing to consider. So before you jump into machine learning, is this problem actually suited to a machine learning solution? And I think there are three key things that you need. So I think the first one is a degree of randomness inherent in the problem. So if you think about randomness on a spectrum, on the one end you have your completely random events, so a coin toss or a dice roll. And it's a waste of time to try and build a machine learning model that, I guess, builds an accurate representation of completely random relationships. On the other end of the spectrum, you have what we would call your very basic deterministic systems. So these are systems that follow a real clear set of rules, and they never deviate from them. But it's in the in-between where you're actually going to get some value from machine learning, right? Where you have a problem with some degree of uncertainty involved, but also some sort of pattern to detect. And hopefully we can build machine learning models that identify what those patterns are and help reduce the uncertainty in our problems. That's where we're going to get value. The next thing you're going to need is problem-related data. Okay, so you need to give your machine a chance to actually find the patterns that are there by presenting it with relevant information. And you're not just going to need some information, you're actually going to need a lot. Okay, because machine learning algorithms are typically slow learners. They learn a little bit off each observation, but over the course of many, many, many observations, they actually start to resemble some sort of intelligent representation of the systems involved and the relationships involved in the systems. Okay, with those two things, you can actually build a machine learning model, but for it to be a solution, you need one last thing. You need the ability to act. Okay, and often this is, can we do anything on the back of our model or our forecast or our prediction? Can we take some sort of action to actually change the outcomes and make them more in our favor? Often this is a question of timing. So can we actually get, I guess, a prediction well in advance that gives us enough time to influence the outcome? But it can also be using a machine learning solution to better understand the key drivers of success and favorable outcomes and try and ensure that we maintain the conditions that result in, I guess, a greater likelihood of better outcomes. So at Transferwise, we actually have a number of different problems that qualify, okay, for machine learning solutions. And I don't want to touch on any in great detail here, but I just want to say that they're all very different, okay? So they require very different approaches when solving them. We have a lot of other ones as well. There's been like talks on automated CS, and that's definitely like something that's very exciting. So we have plenty more than here. But today I want to focus on one in particular, and that would be a subset of predicting user behavior. Okay? So today we're going to look at how we approached solving this problem of user retention, which really aims to get to the bottom of which of our customers are going to keep using our service in the future and which of our customers have not. And this might sound like a really basic question, and really depending on what kind of service you're operating in, it can be. So if you're in a subscription-based service, maybe you get some very clear signal, right? So somebody stops paying their subscription or they cancel their membership, and you know that they're no longer using your service. But in our case, we offer a service which is there for people to use when they need it. And they don't actually call up and tell us, I'm never coming back, I'm never using your service again. They don't delete their profiles. They simply just stop using us and disappear from our data records. Okay, so it's a little harder for us to actually say with certainty whether or not somebody's still using Transferwise. All right, well, what makes this problem suited to machine learning solution? Okay, I think we tick all of these boxes. So we have some degree of randomness. Each customer uses our service for their own needs, but we have very different customers who have very different needs. And as a result of that, they stop using our service for different reasons. So there's some randomness there. But the fact is that they stop using our service for a reason. So there should be some sort of a pattern to detect. Okay, that's simple enough. We've got lots of problem-related data. We keep accurate records of all of our customers' transfer behaviors and their past records, right? And we have plenty of customers. We have over 2 million customers, and we've facilitated over 30 million transfers to date. So we're in good shape in terms of the amount of data and the amount of problem-related data that we have. Do we have the ability to act? Well, we think we at least do in some of the cases, right? There should at least be some reasons that are addressable by us, so some things about the experience that we can improve for our customers. So I think now we've decided that we're going to take a machine learning approach. A good starting point is how do we actually frame this as a machine learning problem? Okay, and I just wanted to illustrate how we think about creating the training data for this sort of problem. So we're just going to focus on what the training set records would be for a single customer. And first, let's give her a name. Let's give her a nice name. Let's call her Trin. Okay, so Trin registers a profile at a certain point in time. And from that moment, we can start observing her at different points in time. Right? We can actually observe her at any point in time up until today, which is represented by this marker on the far right. Okay, well, we've got two timelines here. The top timeline aims to reflect the data that we start to uncover and learn about Trin over time. Okay, so these blue records here represent transfers that she's made. So already you can kind of see that over time we start to learn more about her past transfer behavior. We can start to see how consistently she was making transfers, what kind of frequency she was transferring at. But we learn other things as well. We might learn that she's changed her address, so maybe she's moved country. We might learn that she started using our mobile app, or that she owns a business because she's created a business profile. Okay, and then we're constantly trying to map this data that we have available about Trin and all of our users to some sort of future outcome. And the future outcomes are reflected on the bottom timeline. Right? So you can see here, we're always interested in predicting whether or not she's going to make another transfer, or perhaps when that transfer is going to be. But I just want to talk about the response a little bit. So if we freeze this animation here, we can actually see that this is quite clear, right? Trin does use our service again, so we should flag her as somebody who's still using Transferwise at the observation date. Now this is the easy type of observation. But what about if we freeze things here? Can we say that Trin has stopped using Transferwise? Well, we can't say that with certainty, right? Because all we can say with certainty is that Trin hasn't made another transfer since the observation date. We can't observe what happens on the other side of today. And so this presents a challenge, and it's known in these types of problems as censoring, right? So we have to be able to work with censored response data. We've got two different types of responses that are telling us slightly different pieces of information. So if we want to solve this problem, we're going to have to overcome or figure out a way of working with both types of outcomes. Okay, well, I'll take you through two different approaches that we could use. The first one's what I would refer to as the window approach. And I would wager that in 95% of cases, this is the approach that gets taken. Okay, it's pretty simple. We draw a finite window into the future from our observation date, and we denote outcomes as positive if we observe an event in the outcome window, and negative if we don't. And here we've limited the amount of future that we're considering, so we can actually remove the problem of censoring, right? We're only working with outcomes that we know with complete certainty, and they're all the same. All right. Well, that's nice because it simplifies the problem very nicely. It just becomes a very simple binary classification problem, and you can use your favorite binary classifier on it. But is it reasonable for us to expect our customers to all transfer according to the same sort of window, right? To fit one window for all of our customers? Well, in our case, it isn't, right? Because we have some users who are sending money back home to support their families. And maybe, they have a high level of frequency, so maybe some sort of window would fit them. But then we have people who use our product irregularly, right? Only when they need to. So somebody who's supporting their child who's studying abroad might make far more irregular payments. All right. The other thing to notice here is you might have noticed that the latest observation date that we can actually take a reading in terms of building our training set is at this point. And this actually means that we're not using all of our data, right? Because if we extended the observation date, the outcome window is now extending into the future and we can't observe it fully, right? So it defeats the purpose. But we're not using all of our data, and that's a bit of an issue, right? Because we know machine learning problems love to use data. And not only that, we're not using our most recent data points, and often our most recent data points are our most valuable data points because they're the ones that are most reflective of the current circumstances and conditions. And the other thing is, what size window do we draw here? I mean, if we lengthen the outcome window, then we're just exacerbating this problem. Okay, well, In some cases, this approach might actually be reasonable. If there's an objective outcome at the end of the time window, sure. If you can expect people to all behave according to how you're specifying this time window, perhaps, and it simplifies the problem, reasonable approach. In our case, it didn't really fit the problem that we're trying to solve. So we took a different approach. And we took an approach that I would refer to as the distribution approach, where at each point in time, we're actually asking our model to output a probability distribution for when it expects Trin's next transfer to arrive. Okay? And the nice thing about working with a distribution for this problem is that we can actually assess the performance or the quality of our predictions under both sets of response, right? Force-censored and uncensored observations. Because now in the case of uncensored observations where we observe an outcome, we can just hope that our model is saying there's a high likelihood of observing another transfer at that point in time. And when we don't observe a transfer, we want the distribution to stay low, okay? But we can also get some feedback from our model as to what was the probability it suggested of us observing an event over any window length. So already you should start to see, hopefully it's clear, that we have a bit more flexibility here with our approach. And we're going to talk a little bit about how we do this in a second. But just to recap, defining the outcome is really important. And this is a really important opportunity for you to preserve the nature of the problem that you're trying to solve. So there are two approaches that are generally taken when it comes to churn problems. The first is the window approach, which is simple to implement and could be appropriate if the window is an appropriate assumption to make on your customers. The second is a distribution approach, right, which gives us the ability to predict the likelihood of an event for any time window. It's already more flexible. But also has the added bonus of us being able to retain all of our data for training, which is huge. And we don't need to arbitrarily specify what window length we want to look at and use. Okay, well, how do we do it? So first of all, we need to figure out a way for our model, to instruct our model to output a distribution, okay? And distributions are actually quite nice to work with in terms of an output. Rather than a point estimate, we can output a distribution. It's far more flexible. It tells us far more things. And it turns out it's not actually that difficult, because distributions are generally, the shape of them is dictated by a handful of parameters, depending on which distribution you want to use. In our case, we used the Weibull distribution, which has two parameters, alpha and beta. Alpha defines where the peak is going to be in the distribution, so the location. And beta represents the height of that peak, or in other words, how confident our model is that we'll observe an event at that point in time. And if our model's learning the right things, well then we should observe peaks, so it should push the height of the distribution up at the time that we observe events, so that's the case, that's how we'll assess it for uncensored observations. And it should push the mass of the PDF to the right of today in the censored cases, because effectively that's our model telling us there was a low chance of observing an event over a period of time, which we didn't. So that's consistent with what we observe. All right. Well, in order to do that, we actually need to do one thing, which is to implement a conditional loss function. So this is getting into the guts of our algorithm and actually instructing it as to how it should be assessing each of its predictions. And because we specify how it should assess them, it'll try to learn to make better predictions based on this criteria. But we need to instruct it to assess two different types of predictions in two different ways. So we need to tell our model what the y-actual is, so what the relevant measure of time is that it should concern itself with. So in the case of uncensored observations, that is how long until the next attempt arrived. And in the case of censored observations, that's how long did we not observe an event for. We also need to specify whether it's working with a censored or uncensored event, right? So that's y actual and u here. It's outputting alpha and beta. So we actually trained a very simple neural network with an output layer of size 2. One for alpha, one for beta, right? And if it turns out that we can actually simplify our conditional loss function in the way that we've done in the return function here. So if anybody wants to implement this, you can borrow this, and if you implement this conditional loss function, your algorithm should actually learn the behaviors that we described on the page before. All right, cool. So at this stage, we should be able to train a model that does fairly well. And then we should be able to arrive at a fairly robust solution to our problem. But now we want to go from solution to solving the problem. And this is all about things like implementation of the solution. But also, earlier I mentioned that maybe we'd be able to reverse that equation from before and actually achieve results where the solution is actually more impactful than the problem we originally set out to solve. And so I'd encourage everybody here, once you arrive at a solution, to ask this question. Can it help me solve many problems beyond just the one that I built it to solve? And if you've designed it flexibly, well, then I think the answer to that question is more likely to be yes. And you'll be able to find other problems that you'll be able to solve with your solution, or by implementing it in a slightly different way, if it's flexible enough. Okay, so just to recap on what I've talked about today. When going from problem to solution, it's important to determine whether or not the problem first qualifies for a machine learning solution. Ask yourself those 3 questions. If you can answer yes to all of them, proceed. Define the problem in a way that preserves the core aspects of it. So don't modify your problem too much to make it easier to solve, if you can avoid it. And sometimes you have to tailor the loss function to solve these problems. Retain as much data as you can for training. It's an obvious one. Then going from solution to problem, ask where else can this solution be applied? And I think if you've designed them flexibly, then the answer to this question will be many places. Thank you very much.
How do you distinguish if users stopped using you because they don't like you, or simply the service is not needed anymore?
Yeah, absolutely. Great question. So we have a number of features in the model that we trained that kind of represent, I guess, the customer experience of their past transfers, and in particular their latest transfer. So we can actually interrogate our model and try and understand what the key drivers of churn for any specific user have been. We can understand whether or not, if we played with their experience features a little bit, that their likelihood of churn would have reduced substantially. And that's one way that we kind of use this to uncover whether somebody's left us for reasons of having a bad experience, or whether or not they've just not needed to use our product. And people who don't need to use our product, that's not our problem to solve, right? That's really not a problem for us at all.
And one more related question.
Yeah.
If you have guessed user will stop using your service, how you find out how to retain him or her? Maybe it's more marketing question, but still.
Yeah, absolutely. So, I mean, the marketing team is the team that is really going to run with this solution, and they're constantly trying to experiment about different ways. Obviously, we like to treat all of our customers fairly, but in some cases, it's possibly going to be possible to win them back, right? If we know that we've done something wrong on our end, then we can possibly try to make amends and offer them, maybe like another free transfer or something along those lines to just try us again and see how our services improve. So if it's something where their last transfer took a long time for us to process, well then, once we've improved that aspect of our service, we can go back and try and kind of show them firsthand that we've done that. So there's a constant feedback loop, I suppose.
And how successful have you been so far with predicting the churn, and do you have some retrospective data?
Yeah, so it's doing quite well. I mean, because we actually can't ever know with certainty whether somebody has stopped using us or they just haven't needed to, we I guess, measure the performance of this model based on how many of the people that we marked as churned actually used us again without us doing anything. And those are incorrect observations, or I guess classifications for us. And yeah, the early results are quite positive. So that's happening in some cases, but it's a small percentage.
It's still worth dealing with this issue.
Oh, absolutely. I think this is one very clear way that we can better understand, I guess, what's important to our customers, and I guess try and improve, those aspects of our service.
Absolutely. And the most important question is actually about your hobby project.
Okay.
Please tell us about your project in fantasy sport AI. Is it about video game or something more general?
Right. Yeah, so I think you also mentioned that I'm a big basketball fan. Fantasy sports is this concept where I guess like players play in real life, their sporting match, and then how they perform in real life is actually recorded statistically, and other people can own certain players and compete in leagues where the real life performance actually affects these virtual leagues. So it's all about predicting, I guess, like which players are going to perform well in any given context. It's been a very long-running hobby project for me, but yeah, super valuable. If anyone wants to know more, please come chat later. I'm more than happy to talk about that.
Yes. Thank you.
Yeah. Great.